Welcome. As you could see from the title of the video, we're venturing into a new topic, and that is acids and bases. Now, the reason I chose to start with acids and bases over kinetics or chemical equilibrium is if you can understand how an acid base works, well, because what we are going to learn for most of probably 1/3 of the remaining time in the coursework has to do with buffers, chemical equilibrium, titrations, okay? All of these require a very concrete understanding of acids and bases. And then we're gonna tie in the idea of chemical kinetics, because I think chemical kinetics works better if we can do it in conjunction with thermodynamics, because kinetics does involve a lot of temperature related variable. So I felt if we start with acids and bases, we can nail down quite a bit of concepts as they are all so interrelated. Okay, some of it you may be already familiar with, some of you are not. So this first video is just going to walk you through, well, if you've never heard a serious discussion on acids and bases, then this video would probably get you started on the topic, because that's, again, you have to start somewhere, and I felt the content that I'm presenting in this particular video is sufficient enough to get you moving forward, okay? And then in the next video, we're gonna do something that you're already familiar with, because you all have done a titration lab and a post-lab activity attached to that lab as well. So you might find actually this material probably easier to a certain extent, and then things might get complex again, where we may have to step back and take things a little bit slower. All right, without further ado, let's get started. Well, first we need to define what an acid and base is. So what is an acid and what is a base? Well, I wish the answer is quite straightforward, but apparently it is not straightforward, as at least there have been three big theories that have been put forward surrounding the concepts of acids and bases. And while two of them share somewhat of a similarity, one of them takes a completely different direction on defining an acid and a base. So, which means we have three different definitions of what an acid is and what a base is. So we're going to look at the three theories, okay, and then we're going to put them back in the context of these arrows and, define the acid and a base. Okay. These are the three major theories, as I pointed out. The first one is Lowry-Bronsted theory. Some people say Bronsted-Lowry theory. Doesn't matter which order you say. And Lowry-Bronsted is probably what we're going to be swirling around back and forth several times throughout this course, because the concept of chemical equilibrium, I think, is captured well by Lowry-Bronsted. So that's one of the major theories we are going to focus, at least in this coursework. And Lewis acid-base theory is something we're going to come back to once we have completely finished up with Lowry-Bronsted. And then Arrhenius acid-base theory is fairly simple, and that's the first one we're going to kind of wrap up before we get deep into Lowry-Bronsted, because we're going to be on it for a while, and then we're going to wrap up the big umbrella of acids and bases with Lewis acid-base theory. So what does Lowry-Bronsted say? Well, according to Lowry-Bronsted, an acid is any substance that donates a proton. Pay attention to the terms I use. I use the word donates, okay, and accepts proton. Okay, we're going to see in a minute what is this proton actually looks like. Okay, so according to Lowry-Bronsted theory, an acid is any substance that donates a proton, and a base is any substance that accepts a proton, right? Now, as I said, Lewis acid-base theory takes a completely different direction, and all these theories were created for a reason, okay? because there were shortcomings with one of the theories. So somebody else comes up with the second theory to address some of the shortcomings, but they also leave a trail of shortcomings, and the cycle goes on. All right. So Lewis acid-base theory was kind of designed in the context because Lowry Bronsted left some shortcomings in the theory. And according to Lewis acid-base theory, an acid is a substance that accepts an electron pair, and you will see that, okay, accepts an electron pair. Now pay attention to the terms. That's why I kept it very simple, okay? 3 words, 2 words, so that you can focus, your eyes can focus on the key words here. Accepts an electron pair means a pair of electrons, okay? This is a pair of, okay? So accepts a pair of electrons, okay? Okay. And then a base is one that donates an electron pair, okay? Now, Arrhenius theory is probably something you may have in a way familiar with it. An acid is one that generates a proton. Now, keep in mind, there's a difference on how I'm using my terms, right? When we discussed Lowry Bronsted, we said an acid is a substance that donates a proton, right? But according to Arrhenius, an acid is a substance that generates proton, and a base is a substance that generates hydroxide ion, okay? If you have already forgotten, this is hydroxide ion. I'm going to write this because I don't want to dwell on it too long, but we have discussed this when we discussed polyatomic ions in the context of naming when we were discussing this content in Chem 170. Okay? All right. So what is a proton? Well, a proton is a hydrogen with +1 charge. It's just that simple. So whether we look at Lowry Bronsted theory, which we're going to spend a considerable amount of time, and we're going to start off with Arrhenius acid-base theory, we have to understand the purpose of a proton, which is H+. But since we're going to start off with Arrhenius acid-base theory, we also need to understand the purpose of a OH-. So let's summarize everything on the screen and what an acid is. If you're defining it from a Lowry Bronsted perspective, which is what the LB stands for, an acid is a substance that donates a proton. An acid is a substance that accepts an electron pair if it's Lewis acid-base theory, and it generates a proton if you're speaking from an Arrhenius perspective. Okay? And what is a base? According to Lowry Bronsted, a base is a substance that accepts a proton. From a Lewis theory point of view, it donates an electron pair. And from an Arrhenius theory point of view, it generates an hydroxide ion. Okay? Now, I don't know how far I want to go in testing you on this, but you can definitely expect some kind of a multiple choice question on this topic, because this is kind of very important, okay? No matter which standardized test you take outside of my class, if you don't know what's on the screen that you're looking at now, and there's a problem, okay? And if you have an A in my class and you cannot reflect this back, 2 or 3 months down the road, or perhaps a year from now, then we have a problem at hand. So try to watch this video again. Again, I'm trying to keep the time within 10 minutes, okay? Now, the list of acids and bases is very long. So it's practically not possible for any one person to just remember all those acids and then categorize them as strong or weak in their head. Okay, that's just not possible. And if you can do it, kudos to you. But I don't really see there's a purpose to doing that. Okay, so what I'm going to do is give you the 6 strong acids. Now, you do have to memorize it. I'm sorry, I am not going to give you the 6 acids in the back of the appendix, because, come on, given the list of things I expect you to remember, which is very, very minuscule, remembering the name of 6 strong acids is not that hard. Okay, now you do have to remember these, both the formulae and the name. I am not going to quiz you, but to really move forward in this topic, you have to know what your strong acids are. Okay, there are no exceptions, and I am not going to provide this information. The reason being, if you remember the 6 strong acids, if you're working with Lowry-Bronsted or any kind of other theories, if the acid given is not one of the 6, by default that acid is weak. So there's more weak acids than strong acids. So it's practically not possible for one person, as I said, to remember every single acid. So if you remember the 6 strong acids, if the acid given is not one of the 6, well, that should tell you that it's a weak acid. Okay. Similarly, strong bases. Now, I won't quiz you this way, but there's ways for me to test you to relate your Chem 170 material. Now, strong bases are group 1 and group 2 hydroxides. Okay. Now, as I mentioned, hydroxide is OH minus. Okay. And what is group 1 and group 2? Well, that's why I have the periodic table. Remember our 1A and 2A? Well, it may seem like a long time since you've looked at it, but elements under these 2 columns, when they react with OH minus, they produce strong bases. Okay, I have given a few examples. Let's say one way I would have you do this is in the context of a titration problem. I could give you strontium hydroxide, which is a strong base. I might just give the name instead of a formulae, and you know how to do it. Well, hydroxide is OH minus. Okay, strontium is in group 2, so we know it's 2 plus, right? So we swap and we get strontium hydroxide. So you do not have to memorize which ones are strong bases. All you have to remember is group 1 and 2 hydroxides. You see I have purposefully left out hydrogen because hydrogen would lead to water, which is a weak acid and a weak base. We'll get to that in just a minute. But all you have to remember is group 1 and 2 hydroxides. That's all. Anything with the metal, sodium, lithium, potassium, strontium, or barium hydroxide, okay, all of these are strong bases. So if you know your base does not contain, well, weak bases are actually quite easy to identify because there aren't as many that we use in a chemistry class compared to a list of strong acids and strong bases. Okay. So some of the common weak acids are, well, nitrous acid, acetic acid, and usually the problem would tell you what you're starting with. And so you may not even have to remember these formulas, but you have to know whether the acid given is weak or strong, because that's kind of very foundational on determining how your problem is going to pan out, especially when we get to Arrhenius theory and Lowry-Bronsted theory. Okay, weak bases, ammonia, you know, the liquid that you use in your laundry, ammonia. Okay, amines, any of the amines are, these are amine categories. They're all weak bases. Okay, like I said, I have not given an exhaustive list because if your base, which contains OH minus, if it's not attached to any one of these, that means it's possibly a weak base. Similarly, if one of this is the 6 strong acids that you have to memorize, yes, memorize. Okay. So if the acid given is not one of the 6, that should tell you you have a weak acid. The question might say, okay, so and so acetic acid is used. Well, you know the formula and the name, but you still have to know whether it's weak or strong, because that's the whole point of the reminder. Like I said, 1/3 of the coursework that's left. Okay. All right. The last piece that I want to introduce you to is water. Water is such a unique substance. It's called a universal solvent for a reason, because water is amphoteric. What does that mean? Means it can act as both an acid and a base. Okay, water is such a unique substance. Okay, no matter where you go, what you do, a common solvent that's used in chemistry across the board is water. That's because water is such a universal solvent, and it's amphoteric, means it can behave both as an acid and a base. You will see this when we get to a special case under Lowry-Bronsted theory. You will see that when what I'm talking about here. But for now, just remember this word. Water is amphoteric, means it can act as an acid and a base. Okay. All right. So something we have not paid much attention, even though we've worked with a lot of chemical equations, something we have probably focused, I mean, not that was not our focus, was what are the minimum components of a chemical equation that you need to pay attention to, that actually changes the way you approach the problem. Okay. Are all the reactants and products labeled? Okay, these are the 4 categories that your reactant or products should be labeled: aqueous, solid, liquid, and gas. Okay, now for the big part, what is aqueous? Okay, some of you may already know the definition, some of you never heard of the word, but you'd be surprised that so many people get out of chemistry or science classes but still don't know aqueous, and it's not very good. All right, aqueous means any substance that contains a large amount of water, or in other words, any substance that can easily be dissolved in water. Okay, for instance, you get your saline solution, right? It's got sodium chloride dissolved in water. It's only called saline solution because you're able to dissolve the sodium chloride in water. And going back to our definitions of molarity and molality, your solute is always going to be small amount. Your solvent's always going to be large amount. Going with that idea, in aqueous is any system that involves water. What I mean by involving water is a larger component of that system, which is your solvent, and your solute is always present in small quantities. Okay, or a substance that can be readily dissolved in water. Okay, if your substance is completely immiscible with water, you can call it aqueous. Now, if you remember, let's say you're driving around a puddle of water and the rain has just stopped, and you see spectrum of colors on the water that's from the oil that's immiscible with the water, because it doesn't mix, the oil doesn't mix with the water, and when light shines on it, it produces a spectrum of colors. Okay, now that's not aqueous because the engine oil that's dripped into that water is not dissolving into the water, so we can call that aqueous. Okay, because there's water and there's engine oil, the whole thing is not aqueous because it's not dissolved. So that's why I gave both parts of it to see you'll understand it. Okay, so you should, whenever you're given a chemical reaction from now on, at least until we're done with acids and bases, you've got to pay attention, make sure all these components are present. Is the equation balanced? I've told you that a million times. I would never give you a balanced equation. Unless the equation is self-balanced, then that's the only time you will see a balanced equation. But I still won't tell you whether it's balanced or not. It's your job to figure it out. So is the equation balanced? No, then you must be able to balance it before you proceed. And the third thing is something a lot of people take it for granted and use it as they wish. Okay, now a single-headed arrow between reactant and products has a different meaning than a double-headed arrow. Okay, a single-headed arrow means the reaction goes to completion, which we are going to see shortly, the effect of both the arrows through an examples that we've already learned in 170, but we are revisiting because we are on the topic of acids and bases. A double-headed arrow indicates a reaction leads to equilibrium, means reaction is 50-50 or 60-40, but it's never going to completion. All right, you will make some products, but the products in turn would start to go back to reactants, and the reactants would go back to products. That is one of the main reasons why I started with acids and bases, is because it provides that great opportunity to talk to you about equilibrium rather than talking to equilibrium as a separate topic, which will not make any sense. So it's important you pay attention to the arrow. Okay, the arrow is everything. All right, sooner or later you will not see a single headed arrow for a while in the course. Okay, so when you see reactions with single-headed arrow, it's a positive thing, because the problem is very, very simple. The moment you start to see double-headed arrow, things tend to get more complex, and chemistry is not so straightforward at that point. So pay attention to that. All right. Well, I do want to point out something, because what does this all mean is a great deal of reactions that we encounter or happens around us in the environment are all reactions containing double-headed arrows. For instance, you've all probably heard of acid rain, right? So that sulfur trioxide coming out of coal combustion, okay, when it reacts with water, okay, it produces, you know, SO42 minus plus H plus, and SO42 minus is what's in your sulfuric acid, because think about it, your sulfuric acid is H plus and your sulfate is 2 minus. When you swap them, you get H2SO4, right? Now this equation is not balanced, but that's not the focus of this particular equation. What I want you to see is this is what comes out of a coal combustion, okay? When you combust coal, this is what comes out, and it reacts with the moisture in the atmosphere, and it comes back down as sulfate, which again can react with any moisture that you come across and can generate acid rain. Okay, but this is the basic equation, and you see the double-headed arrow. Okay, and so when this reacts with, like, say, marble, in which is calcium carbonate, then that gets degraded. The marble no longer keeps its texture, and that's kind of the problem. So what I want you to take away from here is, I don't want you to remember any of this equation, because most likely I'm not going to test it this way. Okay, but you see the effect of equilibrium that has on our environment. Okay, so a great deal of reactions are equilibrium. So I'm going to stop here, and then when I come back, I'm going to start off with Arrhenius acid-base theory, and then do some problems that you're already pertaining to it, but I'm revisiting because some of you didn't have a concrete understanding of it, and I know that you don't. So we're going to do that again, because we'll be doing some more titrations in the lab, and I want you to be ready for it. All right, so stay tuned.